All right. We're moving on to our second section of chapter 2 today. And today we're going to be talking about similarity. Similarity is going to come up a ton in this chapter. In fact, it's one of the big key concepts of the chapter. So today we're going to define what similarity means and start looking at some examples of similarity. This is going to connect to our future lessons where we're going to start really getting picky about, I'll show you two figures that have some numbers on the different sides and angles, and you're going to have to tell me, are these two triangles similar to each other? And there are some there's a long way to do that, and then we'll learn some shortcuts because the long way is kind of tedious. But we won't get into the nitty-gritty of all that today. The main thing we want to do is I want you to know what it means for two things to be similar. And if you see two shapes that are similar, I want you to be able to look at them and say, those two shapes look like they might be similar. So define and recognize. And then also to write and solve proportions. And again, I'm super thankful for you asking that question a moment ago about number 6 in our assignment. 6D was a proportion. Now, we didn't have to write any of those yet. We're going to actually be writing those equations today. But now you guys know how to solve it by cross multiplying. And if that wasn't super clear to you, we'll be seeing some more of those in a minute. So before we get started, since similarity is kind of the main thing, do you guys know what it means if I say two things are similar to each other? Mathematically, geometrically. We know what it means in English, right? Similar means what? Kind of close to the same. Yeah. They've got some matching characteristics. Not exactly the same, right? Not exactly the same. If I said, I saw two people in the hallway, they were walking next to each other and they were dressed very similarly, that doesn't mean they were wearing the exact same clothes, right? It means that they were kind of looked sort of the same. Do you guys know what it means mathematically? If I give you two shapes that are similar, what's it going to mean? Any ideas? What do you think?
They could be the same shape but like different sizes.
Yeah, that's exactly what they mean. Yeah. So similarity, we're going to take some notes on this in a minute, but the big idea is that they're the same shape. They don't have to be the same size anymore, but they got to be the same shape. Okay, so two figures that have the same shape, but not necessarily the same size. So let's go ahead and get into it here, folks. Here we go. So we're going to work through a few problems here. This is kind of build out and define what similarity means, which we've kind of got an idea about that right now. Let's just go ahead and work through number 11, part A. This says in 3.5, this is one of your assignment questions. You guys remember doing that one? We were just looking at it a moment ago. That was the one where you had to plot the vertices and draw a triangle. So you drew a triangle and then you dilated it about the origin, and basically this was the answer to 3-5. So hopefully this looks familiar to you. All right, so they're introducing another vocabulary word here. This word corresponds. We've seen corresponding angles already. I want you to try and make a connection to that. The question here says, which side of triangle A prime, B prime, C prime, so they're talking about the big one, corresponds to side CB. So if I look at this smaller triangle, I'm going to go ahead and just outline it in red here and compare that to the bigger triangle. Which I'm doing in purple. Which side of the bigger triangle corresponds to this side right here, this side BC? What do you think? Ideas? When you name a side, you're going to give me the letters at both ends of it. Can you close up your laptop while we're going over notes? Thanks. Well, write down what you think here. If I were to ask you to look at these two triangles and tell me which side matches CB on the big one, let's say it's going to be this one, right? This is the one that matches up with it. So we would call that B prime C prime. Which side corresponds to side AB? You know, you can actually do these without looking at the picture. I challenge you to tell me which side corresponds to AB without looking at the picture. Anybody want to guess? Yeah, this is going to be A prime, B prime. It says, what's the relationship of the corresponding sides? How could you get the lengths of one triangle from the lengths of the other? When you did this in your assignment, you started by finding the lengths of each of the three sides. You found that this was 3, this was 4, and this was 5. What they're asking in this question is, without counting, how would I know that this was 8? What's the relationship? It's double, yeah. The corresponding sides, the relationship between the corresponding sides is that they're a factor of 2. We used a scale factor of 2. So how could we figure out the missing sides? Well, if I knew that this was 4, I could just take that 4 and multiply it times 2, and that would tell me that that side was 8. This next one's kind of a weird one. So they notice that AB lies on A prime, B prime. Like those two sides and the two triangles overlap with each other. Same thing with AC and A prime, C prime. But it doesn't happen with BC and B prime, C prime. These two are not on top of each other. There's a good reason why that happens. Does anybody know why? Why do these two sides overlap with their counterparts, but these two sides do not overlap with each other? Does anybody know? What do you think?
Those A prime and B prime, and A prime and C prime, those start at the origin. The A starts at the origin, just like A. So you can't multiply 0 times 2.
I like that explanation. Yes, you talked about A and how it's at the origin. When we dilate things from the origin, we're just multiplying coordinates times the scale factor, right? When you multiply 0 times anything, what happens to it? Does it change? It doesn't change. Yeah. What were you going to say? Something similar to that. So you had also in your mind this idea of the origin. Yeah. So the reason is because one of the ends of these two sides was at the center of dilation. Center of dilation never moves. So that's probably how I would write my answer. A is the center of dilation, which never moves. This next one's a little bit confusing what they're asking us to do, but read over this sentence and see if you can figure out what are they asking here. It's a yes or no answer, but it's kind of hard to understand what they're saying. They're talking about side lengths. Can we get the side lengths of the new triangle by adding the same amount to the side lengths of the old triangle? What do you think? Yes or no? I'm seeing a little bit of yes. I'm seeing a little bit of no. In other words, if I took the original, which I knew was 3, 4, and 5, those of you who did your assignment knew that it was going to be 3, 4, and 5. Is there some number that I could add to all three of those to get my sides for my new triangle, which ended up being 6, 8, and 10? Is there something that we can add to a 3 to get 6, but it's the same thing that we add to the 4 to get 8 and the same thing we add to the 5 to get 10? No, I'd say there's no one consistent number that I could do for that. We would have to do what instead of adding? What do we do to get these? We don't add the same number, we multiply by the same number. So the answer is that no, we can't add the same number, but we could get it by multiplying. All right. This next one we're going to try and do without a picture. It says Monica dilated triangle ABC to get a different triangle. She knows that A double prime B double prime is 20 units long. How many times larger than triangle ABC is the new triangle? And how long is B double prime C double prime? Can I get you guys to make me a picture here? When we run into a problem like this that's got all kinds of different A's and B's and C's with primes and double primes and numbers, this becomes a lot easier if we just take a couple seconds to draw a picture. Here's my original triangle. How did it go? A, B, C. And you already found the lengths were 3, 4, and 5. That was part of your assignment. They're telling us now that we've got a new triangle that we made. A double prime, B double prime, C double prime. So I'm going to draw a slightly bigger one. And they gave us that length of 20. Where's that 20 belong? That's between A and B, right? So that 20 should go here. So when they ask us the question, how many times larger is it, what would you give for that answer? What are we multiplying by to get from this length to this length? Times 4. So it's 4 times as big. I'm going to write scale factor equals 4. That means it's 4 times as big. If you knew that, then would you be able to figure out how big this side was? They asked us what's B double prime, C double prime. What would it be? 16? Because we've got this 4 here, it would also multiply times 4. So C double prime, B double prime, I would say is 4 times 4 equals 16 units. I'm showing all my steps because this is notes. I'm also modeling when you run into similar problems on your assignment, the type of work I expect to see on your page. All right. Can I get everybody to read over the paragraph here in 3-12 and answer the question? Read it over and answer the question. This would be a good time if you've got questions on anything from number 11. I'd be happy to answer those. What'd you all come up with for your scale factor? 3? If I asked you to show me work, what would you do to show me your work? You could say blank times 5 equals 15 and show that 3 works for that. The whole idea is if I've got 2 lengths, the scale factor would be the thing I'm multiplying one length by to get the other one. So I could just show that to show work also. All right. This next one, I was looking at this and I was like, are we going to have space to do this? They're giving us a bunch of zoom factors here. Are we going to have space to make this thing 3 times as big and twice as big and 12 times as big? No. No, they're not. But then I realized that I wasn't reading the instructions carefully. Are they asking us to actually zoom this thing out, to scale it and dilate it? They're not. They're asking us for dimensions. They're asking us for the dimensions. If I were to ask you, how big is this C? What would you tell me? What are the dimensions of this C? Who are my builders in here? Who are my fabricators, my folks that like to make things and build things? Shop class or metals class. How big is this thing? How wide is it? 6. How tall is it? It's 8 tall and 6 wide. If somebody asked me for the dimensions of this thing, I would say it's 6 by 8 units. Have you ever heard of something described that way, size? Like the size of a poster? Or a picture? Or the size of a TV screen? Yeah. So they're just asking us to find the dimensions. So if we took this C and we blew it up by a factor of 3, how big is it going to be then? It's not going to be 6 by 8 anymore. What's it going to be? Yeah, you're just going to multiply both of those things by 3. You would do 6 times 3 to get 18, and 8 times 3 to get 24, and your final answer would be, it would be an 18, I'm going to just say 18x 24, is usually how we write dimensions. And they didn't give us any units, so we would say units. 18 by 24 units. Can you guys find me dimensions for these other scalings of C? You don't have to show the work for each one of them. Just write blank by blank. Times 2 would be what? 12, 16. Times 1. That's not even scaling it. Times 12. Oh boy, here we go. 72 by, what's 8 times 12? I should know that. 96? Kind of seems like your high school math teacher should know their times tables, right? I don't know my 12s. Isn't that terrible? I mean, I can figure it out. 8 times 12. 10 times 12 is 120, and then 2 times 12 is 24. 120 minus 24 is 96. Okay, I got there. All right. Here we go, guys. Now it's time for us to talk about the really important stuff. Remember what our learning target was. Our learning target was about similarity. So we're going to learn about a super important property of similarity right now. I really hope that you guys are going to give me your attention on this, because this is going to be one of the key things that's going to come up over and over and over and over and over again throughout this entire chapter. And this is the idea of ratios and proportions. Okay, so I'm going to kind of give you my version of this instead of reading through. When I look at these two copies of the letter C, if I wanted to compare them, I could do this by doing a thing called a ratio. For example, if I looked at this side and this side, usually we go the second one divided by the first one. My ratio of this thing would be 24 over 8. That's if I'm looking at those two sides. If I look at these two sides, my ratio would be 18 over 6. You guys get the idea of a ratio? So we make it into a fraction. The second one typically goes on the top. Now, what they're asking about in the second part is, are those two things equal to each other? Is 24 over 8 the same as 18 over 6? What do you think? Let's reduce them. What is 24 over 8? What can you divide into both 24 and 8? 3 goes into them. Nope, 3 doesn't go into 8. 4 goes into both of them. Does 8 go into both? 8 goes into 24, doesn't it? What is 24 divided by 8? And 8 divided by 8 is 1. So that reduces to 3 over 1. What does the other fraction reduce to? 18 over 6. It also reduces to 3 over 1. Would you agree that those two ratios are the same? The numbers are different, but when we reduce them, we get the same value. And this is a key property of two things that are similar. If two things are similar, then the ratio of corresponding sides will always be equal to each other. All right? This is a key thing. In fact, it's so key, I'm going to write myself a note up at the top. In similarity, ratio of corresponding sides are all equal. That means if I make a fraction out of this side and I make a fraction out of these two sides, those two fractions better reduce to give me the exact same thing. If not, then they're not similar figures. So these ratios are going to be equal. So I'm going to go ahead and set up this next problem by creating two ratios. I'm just drawing the fraction bars right now. In a moment, we're going to put some stuff on the top and bottom of these things. And since they're telling us that these two things are similar, then I know that these two ratios are equal. I'm going to put that equal sign in between there. When we make an equation that looks like this, it has a special name. It's called a proportion. A proportion is a special type of equation where you have two fractions connected together with an equal sign. Do you guys remember how we solve proportions? We just did it at the beginning of class. Cross multiply, yes, good for you. Let's go ahead and fill in our proportion. So one of our ratios is going to have these two numbers in it, because those are corresponding sides. And usually we put the new one on the top. So can you guys please pick one of your two fractions? Doesn't matter which one we do. And get 8 and 20 in the top and bottom. 20 on the top. I'm going to put it in this first one. And then we also have some information about the bottom of both of these figures. 6 and x. Now I don't know what x is right now, but that's okay. We're going to find it in just a moment. Could you please fill in the 6 and the x? And again, remember that convention. Usually we will put the new one on the top. 6 and x. X is the new one, agreed? Do we have enough information to figure out what x is? Do you have tools that you could use to solve that equation? We just mentioned it a moment ago, cross multiply. Can I get everybody to go ahead and cross multiply and get me a value for x, please? Cross multiply. So we built a proportion, now we're going to cross multiply. I've got a 20 times a 6. And an 8 and an x. $20 times 6, I think that's 120. Does that sound right to you guys? And 8 times x is just 8x. So I just need to divide on both sides, and we'll have what x is. We'll divide by 8 on both sides. I'm going to do this in 2 steps. I'm going to divide by 4, and then I'll divide by 2. 120 divided by 4 is 30. And then divide that by 2, I get 15. I want to say 120 divided by 8 is 15. Can somebody confirm that with the calculator, please? Yes, it works? It works, it works. Let's do one more check. I just want to make sure that we're good to go here. Does anybody have any questions about where we got that 15 from? Could you guys rewrite my proportion off to the side? This is just going to be my final check. I'm going to write this as 20 over 8 equals, but instead of x, I'm going to go ahead and put that 15 in there. And I'm going to reach for a calculator here. And rather than reduce the fraction, let's just divide this. 20 divided by 8 is 2.5. And 15 divided by 6 is what? What do I hope it is? I hope it's also 2.5. If it is, then we're in good shape. Hey, it is. I got the same number for both of my ratios, so x must be correct. All right. What do you guys think? Show me on your thumb meter what do you think about setting up that proportion and solving it. You feel like this looks way too easy? Some of you are like, there's got to be a trick here. And I'll tell you there is a trick. There is a trick. So for those of you who got your thumb straight up right now, I need to warn you about something. It is super easy when you're setting these up to flip one of your fractions. And if you do that, you're going to get a wrong answer. That is like the number one mistake when you go to set these up. If I'd put this x and this 6, if I'd flipped them around, I would not have gotten the correct answer. And it is really, really, really easy to do that. Okay, so you want to make sure that you're doing some kind of check at the end just to make sure that you're not making that mistake. Because it's super, super easy to do. All right, that's what I got for you guys today. Do you have any questions for me? So moving forward, we're going to be setting up and solving some more of these. So all these problems, this is what we'll be doing on Thursday. And then after this next section, when we get into next week, that's where we're going to get into the nitty-gritty of how do we show that two things are similar, and then what are the shortcuts for making that quicker for us. All right, folks, you guys have some time to work